All right. I understand as we go, we may have some additional people joining. So, good morning, afternoon, evening, whichever time zone you may be in. And I know that we'll have people joining to watch this after the fact. So, we will be making the presentation available after the meeting. It's going to take us a few days to get everything ready and have that available. It will probably be towards the end of the week. So we'll have a recording of the webinar available as well as the presentation itself available for you. We're going to look at a challenge that's quickly becoming central to the next generation of consumer electronics. That's how to sustain a higher AI performance in devices that continue to get thinner, lighter, and become more power constrained. The issue is simply not generating more compute, it's how to manage the heat that comes with that compute. We're going to discuss the way traditional passive cooling is approaching its practical limits and how microfluidic cooling can create a new thermal headroom without forcing compromises in performance, comfort, or industrial design. As I said, maybe I didn't say this before, but if you have questions that are coming up through the presentation, please submit those online. We've allocated time at the end to be able to answer as many of those as possible. And those that we don't get through, we can follow up with you directly after the webinar as well. I'm going to start with a brief introduction. To introduce myself, I'm Nate Coy. I'm an executive account manager here at Boreas. I work with global OEMs to bring piezoelectric technologies into production across a range of products, everything from consumer electronics to wearables, other compact systems, as well as things in automotive and many other markets. Joining me is Cédric Leclerc. He's a mechanical engineer here at Boreas, and he's leading much of our work into the piezo-driven microfluidics. I'm going to begin covering some of the market challenges, discussing the underlying technology, and system concepts. Cédric's going to then take us into a deeper dive in the more technical aspects such as engineering, performance data, and the integration approach. But first, let's take a quick look at the company and the technology behind the approach. Before we get into the thermal challenge, let me briefly introduce Boreas and the foundation behind this work. Much of the company can be summarized in a few key facts. To begin, Boreas is a fabless semiconductor, and we're headquartered in Bromont, Canada. It's about 60 miles outside Montreal. If you ever get a chance to visit, it's one of those picturesque Hallmark postcard types of towns, so definitely recommend checking it out if you're ever in the area. We were founded in 2017 around a core capability, which is driving piezoelectric actuators with significantly lower power and a much smaller footprint than you find in conventional solutions. Our technology is protected by a strong patent portfolio and is already proven in production. We've shipped in millions of devices across applications, including solid-state controls, haptics, and active cooling solutions. Microfluidics is not a departure from our core technology. It's actually a natural extension of our proven driver technology platform, moving into fluid movement and thermal management. Our proven foundation matters because the thermal landscape is moving so quickly today. This brings us to our central problem. For years, compact electronics have depended primarily on passive cooling. That approach has worked because power levels, duty cycles, and the available surface area have largely remained within a manageable envelope. But today, Edge AI is pushing devices beyond that envelope. The reason is the rapid movement of AI onto the device itself. AI is moving from the cloud onto the device because local intelligence creates a better user experience. First, it responds immediately and is able to protect sensitive data. It works offline and removes the dependence on a network connection, but those benefits require substantially more local compute. Often this comes in very short, intense workloads. The device must not only reach peak performance, it must sustain that performance in a compact enclosure. At that point, we find thermal management becomes a system-level constraint, rather than just simply a secondary design consideration. More local compute creates a direct challenge for today's passive thermal architectures. With passive cooling, heat can be spread, but it cannot be actively directed. As the silicon power rises, manufacturers are forced into three very familiar trade-offs. First, they can throttle the processor and give up performance. Second, they could allow higher surface temperatures and create a discomfort for the user. Or third, you can add heat spreading volume and compromise the product size, weight, and industrial design. In practice, as we look at products, most balance all three of these. Often this results in a device that may advertise impressive peak capability, but it can't maintain it under a sustained AI workload. So what does the ideal outcome look like? Our goal is to break the thermal trade-offs. We want sustained compute without thermal throttling. We want comfortable touch surfaces during extended use and ultra-thin products that don't require a bulky thermal solution. Achieving all three of these does require a change in how heat is managed. Instead of only spreading heat from the source and waiting for it to dissipate, we need the ability to capture it and transport it deliberately to the areas that are best available for rejection. The answer is to bring a proven active cooling principle, but bringing that into a smaller form factor. This is what we mean when we talk about data center cooling in your pocket. It's about bringing high performance computing, which you're increasingly using liquid for active transport and heat rejection, and helping to bring it to where the heat can be more appropriately rejected. Our work brings the same type of principle into compact battery devices using component and power levels appropriate for smartphone, wearables, smart glasses, PCs, and many other kinds of application. Here's what this looks like in a compact device. Boreas microfluid cooling replaces the passive heat spread with a closed loop, actively controlled flow. A piezo micro pump helps to circulate coolant through micro channels, capturing heat near the source and routing it to colder, more usable areas of the device. Because the flow is actively generated, the system is gravity agnostic and not dependent on a vapor cycle. The routing can follow the product architecture rather than forcing the architecture to conform to a conventional heat spreader, such as a vapor chamber. This is particularly important as devices become thinner. Passive structures start to lose their heat transport capability as the internal space collapses. In an active system, performance is driven primarily by the controlled flow through the channels, giving the designer a much more useful level. So here you can see on the slide, you can see the pumps. Our driver IC is not connected here. In a solution such as this, if we're doing samples, it would run from our dev kit. And then you can see the microfluidic channels. And in this particular solution, we have two different colored liquids in there. That allows you to be able to see the flow. Otherwise, it operates so quietly and efficiently, you can't tell the difference between when this is on and off. At a practical level, this solution comes down to three core elements. I touched on those a little bit on the previous one, and we'll deeper dive here. The first is the microchannel cold plate or heat spreader. This is what captures the heat and routes it. The second is the compact piezoelectric micropump that circulates the fluid. And the third is our 1931 driver IC, which provides the efficient electrical control needed to operate the pump. Boreas supplies the driver technology, control expertise, and the integration support while working with pump and thermal partners to fit the solution into the customer's architecture. The layout, channel geometry, and pump configuration can all be adapted to the device, which makes the approach relevant across all kinds of applications from wearables, mobile devices, laptops, and many other applications. With the overall system architecture established, let's take a closer look at our 1931 driver and why its efficiency is so important in compact battery-powered devices. At the center of the system is our 1931, which is an ultra-low power piezo driver. It provides a single channel bipolar output of up to 190 volts, giving us the voltage needed to operate piezoelectric micropumps efficiently. For compact battery devices, the driver solves several important challenges. First, it consumes roughly 10 times less power than competing solutions and generates less unwanted heat and helps to preserve battery life. The wafer level chip scale package is only 2.1 by 1.7 millimeters, minimizing the space required on the PCB. It also starts in less than 300 microseconds, allowing the pump to respond quickly to demand and change the flow. The key point is that we can add active fluid movement without introducing a large power, thermal, or space penalty. On the next slide, I'm going to show you just how that power advantage translates under comparable operating conditions to competing solutions. Here we're comparing our 1931 driver with a competing solution under the same driving conditions, same load, frequency, and peak voltage. The 1931 consumes approximately 64 milliwatts compared to nearly 695 milliwatts for a competing solution. This matters because nearly all the power consumed by the driver eventually becomes heat inside the device. The thermal images make that difference visible. The competing solution creates a concentrated heat spot simply by operating the pump, while the 1931 remains much closer to the surrounding temperature. So in a thermally constrained battery-powered product, it makes little sense for the cooling system itself to become a meaningful source of the heat. The efficiency of our driver allows more of the available power and thermal budget to go towards device performance. The BOS 1931 provides the electrical performance needed to operate the pump with minimal impact on the power, heat, and PCB space. I'm now going to hand over to Cédric, who will begin by walking through the pump operation and heat transfer performance of the complete system. Cédric?
Yes, thank you, Nate, for the technology introduction. I will follow on with a deeper dive into the technology, but first, let's go on surface with how a piezoelectric pump works. So basically, just as a reminder, the piezoelectric actuator works onto a bending principle. So it's basically made out of a ceramic element bonded to a stainless steel substrate or other metallic type substrate. And when you apply the positive voltage, the ceramic expands, and because of the structure of the both materials, then it moves upward. And then when you apply the negative tension, it shrinks and then generating a downward movement. Then if you take that same actuator and put it onto a piezo pump body, then which integrate two check valves, one for the inlet, one for the outlet, you can generate a net positive flow rate with an AC drive voltage. So let's break down to 6 stages. First is the free state. So basically, the pump is at rest, nothing's happened. You have a neutral internal volume. On the intake cycle, then the ceramic expand, generating an upward movement and opening the inlet valve. At peak voltage, you now have reached the maximum cavity volume, and then you will begin the discharge phase, where it pushes down on the volume inside the pump body and opening the outlet valve. The discharge continues, emptying completely the chamber, and then now you have reached negative peak voltage, so minimum pump body volume. And then you repeat that cycle on and on and on with an AC drive voltage generated by the BOS 1931, and you achieve a flow rate that way. So next slide, please, Nate. Now, for applying that to the piezo-driven liquid cooling, it's really basically one simple governing equation, and the driver IC command, it's only 3 variables. In simple terms, the extractions come down to 3 things. You have the mass flow rate that the Boreas IC have control over, Then you have fixed fluid, cooling fluid properties that is set by the requirements for the thermal management team. And then you have temperature boundaries set by the integration. So basically that would mean the SOC max junction temperature, skin temperature, and other limits like the ambient temperature. With the Boreas IC, you have basically full control only over the mass flow rate, and then the rest is fixed by the integration. So that would mean that you can adapt with firmware. You can adapt the cooling loop behavior interaction to system telemetry events, just like you would do with a typical fan system or other cooling means that are active. Next slide, please, Nate. So in terms of heat transfer advantage, with passive solution, vapor chambers are an excellent passive spreader at moderate heat flux in thicker format. But as they get thinner, you get diminishing return, unfortunately. Microfluidic cooling is not bound by the same constraint. From a design standpoint, it's a matter of balancing out the channel layout, the channel cross-section, and the pump operation point when you design this type of integration. Thinner or larger layout will only mean that you higher back pressure that can be addressed by adding either more pumps in parallel in the airing, so you can meet the desired operation point and design in some overhead if needed. By commanding the flow rate in real time with the Boreas IC, you can slow down the flow rate to save on power when needed, or you can overdrive by changing the waveform parameters to achieve on a higher sustained load. Next slide, Nick, please. So now that translates to strategic thermal management advantage. So the active pumping basically buys you control over where the heat flows and where it takes it, depending on the layout of the microchannels. Being a mechanical engineer, so that would give me freedom to precisely route the heat where I want it by design. So you can basically route around thermally sensitive component and bring the heat to surfaces hard to reach with typical passive solution. That would mean, let's say in a device context with a laptop, that can reach back covers, further area that a typical vapor chamber or graphite film wouldn't reach normally. We'll see some example on that later. In this specific case, for the webinar, polymer films can be bent around structures like hinge or curved surface, which can be difficult with a thin vapor chamber, where any crush or pinch would drastically alter performance. The device orientation, it doesn't matter as much anymore. As the pump pressure exceeds any gravity head that could be generated by changing the orientation of the device, it just orders of magnitude stronger than what the fluid would apply with the gravity onto the pump. You're also not bound to a single material for the microfluidic channel, so now today we're discussing flexible polymer-based film, but other options exist too. Rigid copper-based spreaders, tubing, whatever you can push fluid through, you're not limited to. You have a choice over a solution to match your reality. The Boreas IC and piezo pump can adapt to different type of integration. You could also, now we have talked about propagating the heat to a chassis or something, but you can combine the channel layout to other means to extract the heat faster. Instead of just reaching more chassis surface, you can combine that to air ducts with forced air circulation or further located heat extraction means where you have the real estate available in your device. That would mean that you could extract more heat for the same cooling loop. Next slide, Nick, please. Now we will follow. What? Yeah, thank you, Nick. Oh, the other one. Yeah. We will follow with a lab case study that we have done at Boreas in the sample film. Just keep in mind that this is not reflective of a complete integration. It's just a way to showcase the plane heat transfer conveyed by the active pumping. There are basically as many ways to implement the technology as there are devices out there, so we'll present some possibility in the next section. Next slide. So here's the test setup we have done at Boreas just to show for the showcase. So basically, we use a polymer-based cooling film about the size of a smartphone. We have bonded that to a stainless steel substrate carrier with an FR4 composite insulator in the middle, really to insulate the heat source from the surface and really show the heat transferring through the channel. And then we have put a 16 by 16 millimeter heater source onto the film. and then place that face down so the exposed surface is showing to the infrared camera. Next slide, Nate. So here's a quick thermal imaging comparison. So without the pumping active, we have a definite hotspot on the surface, which is not radiating much because of the FR4 insulator. But when we activate the pumping, the temperature drops drastically and it even out around the surface. We've been able to push that up to 6 watt input of the power source, and still there you still have a pretty even surface temperature. Now you can send the third image. You have one side that is hotter than the other. That's basically because of the routing of the film that is a serpentine loop going from the bottom to the top of the image. And then you see the return of the outer fluid coming from the pump and then cooling around the surface before going through below the heater core. Next slide, Nate, please. So here's a thermocouple reading from that same exact test. Just as a note, for phase 1 through 6, from 1 watt to 6 watt, with the active cooling enabled, the Boreas driver circuit power consumption does not change much, is around 70 to 80 milliwatts on average. As the fluid heats up, the viscosity goes down a little bit, so it might impact a little bit the power consumption, but still it's very minimal for the improved cooling you get with that. So open pump activation there, it delivers an immediate 27.5 Celsius reduction at the heat source under a 1 watt steady state load. We have estimated the spreading resistance, and it's pretty even across the board. About 7 Celsius per watt between the heat source core and the furthest temperature measurement location in the surface. And the surface temperatures, they're pretty even across each power level. So we have basically a grouping depending on right above the heater, 2 millimeter across and 70 millimeter across. You have about 2 to 3 Celsius grouping over the surface. Typically with a vapor chamber, we would have a gradient with the hotspot being right above the heat source, and then the more you're further from the heat source, the colder the surface temperature. Yeah, again, this is just an example. The result can differ based on the channel routing and targeted flow rate and the integration, definitely. So that is definitely a case-by-case study in your reality. Next slide, please, Nate. Yeah, so now I'll show some of the example of what where could active microfluidic cooling can be applied, and some examples that we have explored so far. Next slide, Nate. Yeah. So here are some renderings of the possibilities that can open up with microfluidic active cooling. So there's a definite sweet spot with lower TDP devices. So even if the SOC core temperature is high, with active cooling, you can route to a more larger surface area on the device. That's in this case with smart glasses, where you want the user comfort and don't feel the spot right beneath your temple. Then you could route microchannels either into the frame or within a film or whatever type of spreader you want it can be integrated, and then have a much more cooler surface temperature for the user. Another use case would be in RAM sticks. Let's say you build in a metal core into the PCB, then you could route cooling through beneath each of the memory chips, and then have a forced air cooling pushing area onto the fins to extract the heat further. Another nice example of that would be integrated into a laptop. Let's say you have a different hotspot on the D cover below the keyboard. Then for user comfort reason, you don't want that. So you could route a flexible film from the bottom of the laptop to the back of the screen, where it doesn't matter as much to have higher temperature, and then spread the heat extracted to a much larger surface, and then reach more acceptable surface temperature. So the way we would typically approach the problem is by having access to a larger, colder surface to sync to. So you can run either at higher power for the same surface or surface temperature, or you can keep the same TDP level and spread to a smaller area because now you have a much larger area to spread to. Next slide, Nate, please. If you want to put those kind of integration a bit further with advanced manufacturing capabilities, the channel could be built in directly into the enclosure. Let's say you have a device with a large plastic surface. The thermal resistance is high, yes, but you can compensate that with the bulk of it. So basically, routing channels everywhere in the enclosure, then you can have still a good temperature difference between the colder and the hotter side, and then spread the heat across a whole enclosure to optimize the output. Yeah, and I will now let Nate continue for the Boreas Blueprint section.
All right, thanks. We've shown how the technology works and the performance it can deliver. Next, we're going to talk about how to integrate it efficiently into a real product architecture. This is the purpose of what we call the Boreas Blueprint. It's our end-to-end framework for reducing technical and execution risk of bringing piezo-based cooling from concept into production. The reason a structured framework is needed is what we call the piezo integration gap. And this is something we've experienced on the haptic side and is similar on the cooling side. Strong thermal performance alone is not enough. The solution has to fit the product architecture and be practical for manufacturing. This is where many programs encounter an integration gap. The actuator, driver firmware, mechanical structure, and fluidic design all affect one another. If those elements are developed independently, performance can become inconsistent and schedules begin to slip. Closing that gap requires a coordinated system approach from the beginning. This is where the Boreas Blueprint brings these different principles together. The blueprint is our framework for doing exactly that. It brings together the three disciplines: the electrical architecture that drives the pump, the software that controls and optimizes it, and the mechanical integration that determines how the energy is converted into a useful flow. Rather than treating these as standalone components, we provide a validated reference architecture that works across these disciplines as one system. The objective is to move from an initial concept to production relevant prototype in weeks rather than months, while at the same time working to reduce the technical risk. Within the Boreas framework, we have a clear division of how those roles work and what we play in that. On this slide, it defines the role Boreas plays in the overall system. We don't provide a fixed proprietary cooling module. We provide a piezo engine that makes a customer-specific thermal application become active. This includes our 1931 driver, the firmware interface, and the waveform tuning required to operate the pump efficiently against an actual microfluidic load. Because the control platform is geometrically agnostic, it can support different channel layouts, a single loop, or parallel flow paths without changing the fundamental architecture. We also help bridge the pump and actuator supply chain gaps that can happen. If a standard micro pump doesn't fit the available space, we can work with piezo manufacturing partners on a custom piezo pump. The thermal architecture remains specific to the product, and our role is to provide and optimize the engine that drives that. The physical heat spreader is then developed through a clear collaboration model between us, the customer, and our thermal partner. The heat spreader is developed in collaboration, as I mentioned, between us, the customer, and the thermal partners. The customer brings the product requirements such as heat source location, the power profiles, available mechanical envelope, what the skin temperature limits are, and the areas where heat can or cannot be rejected. The thermal partner then translates those inputs into a physical solution that includes the cold plate or heat spreader, the micro channeling geometry, the materials, the routing, simulation, and prototype manufacturing itself. At Boreas, we work alongside both teams to match the pump, the driver and waveform to that microfluidic design, and then we support the electrical integration and the system level optimization. The validation is then shared between the thermal partner that confirms the spreader and the flow path, Boreas, where we confirm the efficient pump operation, and then the customer evaluates the complete solution inside of their device. This results in something that's not an off-the-shelf module. It ends up being a coordinated solution built around the customer's architecture with each party contributing based on its own expertise. At Boreas, we remained involved as that jointly developed solution moves forward towards production. The broader value that Boreas brings is the continuity from the first architecture discussion all the way through mass production. Our electrical, software, and mechanical teams work together as a single point of contact. This reduces the risk of handoff that often exists when you're dealing with separate component suppliers. We also bring an experience moving piezo technology into demanding high volume applications across consumer, PC, and automotive devices. That production background matters because the final solution must deliver something that brings repeatable performance and isn't something that works simply once in a laboratory. We're currently in process of preparing a microfluidic cooling development kit to help teams move quickly from the initial concept to being able to have a working prototype. This kit brings together the complete system. It has our 1931 driver IC. It includes a micropump and the microchannel film shown here. This happens to be one of the PET-based films. This allows teams to be able to evaluate the flow rate, thermal performance, and the mechanical integration in a standalone or directly in your own application if the form factor happens to align. If this is something your team is interested in, we urge that you let us know quickly. We're working to gather early interest, and when the kits become available, we'll be providing those first in line as they are available. We're still working kind of on the scheduling of that, but I'm guessing that could be as soon as the next few weeks. Kind of as a quick summary, we're finding that edge AI is creating a thermal challenge that passive cooling alone cannot continue to solve. Active microfluidic cooling provides a new lever, the ability to capture heat, transport it, and control the performance in real time within a compact power budget. If you're evaluating your thermal limits in mobile, wearable, or computing platforms, we welcome the opportunity to look at the architecture and determine where this approach could create additional performance headroom. We'll now jump into some of the questions. Our marketing colleague, Marc-Andre, has been collecting those, and we can work through some of those and provide answers. As I said before, we'll also, if there's questions that we don't answer here that are shared, we can then follow up directly after this webinar and be able to provide answers for those. Marc-Andre, could you jump into those and share those with Cédric and I?
So hello guys, I repeat, if you have any question about what we present today, feel free to ask them in the chat. We have some question here. Someone wants to know, does Boreas sell the micropump itself or only the driver IC?
So I can jump in on this one. So what you're going to find in production or in scale, what we're doing is we're providing our driver IC and then the microfluidic film, as well as the piezo pump would be sourced directly from those suppliers. In the case of the development kit that we're going to make available, we will be selling a full kit that includes our 1931 driver IC kit, as well as the film and the pump that were shown. We also provide directions for how to connect our driver kit into those pumps. And then we have a Haptic Studio software. It's called Haptic Studio, but really what it does is allow you to customize the waveforms as it goes into driving the pump. So you have a very easy platform for being able to drive that. We'll create some standard waveforms that you can use. Within that, we optimize those waveforms for the pumping movement. And so there's some very specific ways that we drive the waveform and what those waveforms look like. So we'll make those available. And then it becomes very easy for you to customize and control those waveforms as well on your own using our Haptic Studio.
Thanks, Nate. So I have another question here. What happens if the microfluidic film is squeezed or folded?
Yeah, I'll take that one. So basically, for polymer, let's talk the specifics of polymer-based film. Those can be conformed to curved surface and are designed and can be designed for foldable application. Let's say for a foldable phone or a laptop hinge. It really depends on the integrations, the requirements. So basically, this film stack will be adapted to meet that reality.
Great. And have we already tested the number of times that the film can get folded?
Yeah, for past project, we've seen application that we're targeting about 200 K fold and fold cycles. So I think that would be the baseline for that kind of application.
Okay. Someone wants to know, how is the film attached in the device? Is it glued inside the cover?
Yeah, for again polymer film, the thinner the adhesive, the better. So typically it's bonded with the thin PSC film that doesn't have that much thermal resistance at those thickness. So this is something below 50 microns. For other type of spreader, let's say a solid copper base e-spreader, you would attach the heat source and the sink output with gap pads or thermal compound, as you would with a vapor chamber or other conduction-based solution.
Okay, here I see a question. Is the pump audible during operation?
Yeah, I can answer that one too. Typically, the pumps are driven below audible levels. So basically, for the one shown during the webinar, where are typically driven below 300 hertz and below. So you wouldn't hear that definitely. And then depending on the situation, you can drive 300, you can drive below. The Boreas IC really allow to control that on the fly to tune it further.
Okay, and maybe I have one last question here. How much Z height does the cooling loop add to the thermal stack?
Yeah, again, that one, it depends on the integration, but typical film thickness we have worked with so far are around 0.3 millimeter. So, and there is a small local bulge where the pump location typically be below 1 millimeter. So basically, just to give you a rough idea, pumps are about between 7 by 7 millimeters for the smaller one or 10 by 10 for the larger one. So you just need to find a place in the device to place those thicker parts of the film, and then the rest is below 0.4 millimeter.
Great, thanks. That was all the question and I have now for now, Nate.
All right. Well, as I said at the start, you will make sure that the presentation is available towards the end of the week with the recording of this as well. If there's additional questions that come up, and we also know that people would be watching this after the fact, please feel free to reach out to us directly if there's applications where you're interested. This is really a solution that tends to be very customized based on your architecture. It's designed to be able to fit in, find your hotspots, move it to the best location for that to be able to cool. So we're really interested in engaging, talking, finding more about your discussions.
Nate, sorry
Yep.
to interrupt. We have one last question that someone asked, thinking of phone-like use case, does this technology interfere with wireless charging performance at all, Cédric, maybe?
Yeah, typically the polymer films are more transparent than their metallic counterpart, but being a custom solution by design, you can route it around the features that you want to avoid. So let's in this case for wireless charging, you can just route around the surface so you can avoid having anything interfering and diminishing the signal of the wireless charging.
Maybe to add to that, we definitely see, we talk about edge AI and things creating more heat in the device. Clearly, when you've used your inductive charging, that generates a lot of heat. And so, in addition to what Cédric said with kind of the coexistence capability there, that could be a strong potential application for this type of solution as that device heats up, limits some of the charging capabilities. It could give a platform for being able to help move heat away from something like that. So appreciate the thoughtful questions, the opportunity to be able to share our information with you today. Look forward to, hearing from you with additional questions and continuing this discussion offline. So appreciate that, and with that, we'll wrap this webinar up.